Hello everyone. In today's session, we are going to be looking at part 2 of section 1-8. And here we are going to be focusing on linear transformations. I'll be covering the following topics. First, a quick recap of what's a matrix transformation. Then we'll define linear transformations and properties of linear transformations, and then some examples. Okay, so let's begin with the matrix transformation. A matrix transformation is a transformation from an n-dimensional space to an m-dimensional space defined by Tx equals Ax, where A is a m by n matrix and X is a vector in Rn. For simplicity, we denote a transformation which was developed by using this matrix product by this notation. X goes to Ax. It's a transformation, but the thing is, the transformation was brought about by multiplication of a matrix with a vector. In other words, just suppose we have a space Rn and we have a space Rm, and then we transformation, remember it's a mapping or a function. So if T acts on an element of the n-dimensional space, and when T acts on it, it's like basically you're multiplying a matrix A to the vector X to get Ax. So this transformation, which is brought about by multiplication by a matrix, is called a matrix transformation. So this is what we say. Here it is multiplication by matrix A. Okay, some observations. A matrix multiplication is being associated with a transformation. Remember, a transformation can be a function or a mapping. Now, for every vector in the n-dimensional space, Tx is computed as A times X, or it's a product of a matrix with a vector, where A is a matrix of size m by n. Now, so keep this in mind whenever we are talking about a matrix transformation, that the domain of this transformation is an n-dimensional space, which is basically this n-dimensional space has connection with the number of columns the corresponding matrix A has. And the codomain of T is Rm when each column of A has m entries. Okay? Now the range of T, it is a set of all linear combinations of the columns of A. Notice that when we write Tx equals Ax, now Ax is a vector in Rm, so we can write Ax here. Remember, Ax can be written as a vector in Rm. So B, if you look at this matrix equation, so look at this Ax equals B. I can write this as a vector equation where it is A1 x1 plus A2 x2 plus dot 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 plus an xn equals B. Now these AIs, remember, are the columns of the matrix A, and they're going to be n columns of that. So B, when I say the range of T, it means all those elements in Rm which can be written as a linear combination of the columns of the matrix A. Now let's look at a very simple example, and we have done this previously also, and it's a very simple one. If A is a 3 by 7 matrix, what must be the A and B in the corresponding transformation, which is a matrix transformation, defined by Tx equals Ax. So remember, my A is a matrix of size 3 by 7. So the corresponding matrix transformation is going to be from R to R. Remember, we just talked about that the number of columns of the matrix A will actually be the corresponding domain of the matrix transformation, and it will be R7, and the codomain of this matrix transformation is going to be R3. Okay, let's talk about a linear transformation. So remember, we have talked about a transformation, which is a mapping, and when that transformation is defined using a multiplication by a matrix, then that transformation is called a matrix transformation. Now we're going to talk about a very important transformation. It's called the linear transformation, a very, very important transformation. Now, what is a linear transformation? It's a transformation, okay? It's a transformation which is going to be linear if the two conditions are held. And that is, T, when acts on the sum of two elements of the domain of T, which are U and V, that is T of U plus V, is the same as T acts on U and T acts on V separately, and then you add those two elements. So this is T of U plus V equals TU plus TV. And second one, T of CU, okay, here. So this is CU, small u guys, is C times TU for all scalars and all U in the domain of T. Now, these elements which are in the domain of T, we also call them vectors. It's a terminology, guys. Okay, so this U and V are also called vectors. Do not confuse them with always that vector in Rn or Rm. Here, when I'm talking of a transformation, I'm talking of a transformation from one set to another set. And the elements in the domain of T, I'm saying they are vectors. Okay? And if those sets are n and m dimensional spaces, then definitely there will be a n dimensional vector and a m dimensional vector. But at this definition, very important to keep in mind that this is a linear transformation. I am looking at a very abstract definition. Okay, so when I say that U and V are vectors, or I can also say U and V are elements, are objects in the domain of T. They're just present. So for example, if you have little, I have a set. So my set has element U and V. That's what it is. So if I have an element U and V, then when I add these two, so what this, okay, let me explain it in a more clear manner here because I need a little bit more space. And okay, let's look at this one. Okay, this is vector U, this is vector V. Now when T acts on this, and we're going to explain what this T of U plus V is basically doing. So when T acts on U, it takes us to an element TU. When T acts on V, it takes us to the element T of V. Now, what this condition is saying, when T acts on U plus V, okay? So my U and V will be another vector. So U plus, okay, let's, okay. So coming back here, so I'm having a vector now. I'm adding U plus V. So I get a new vector u plus v. So when t acts on this vector u plus v, it takes to another vector which is exactly the same as when you're adding tu plus tv. In other words, it is preserving the structure. If you're adding two elements in one, and then when you look at their elements of tu and tv, basically you're adding those elements actually. That's what it simply means. So this, in the terminology of linear algebra, it says linear transformations preserves the operation of vector addition. That's what this whole thing means. Okay? Now, let's look at the next one. T of C of u. It means when t acts on a scalar multiple of u, it is the same as you're multiplying the scalar to t of u. Now, this is true for every scalar and every u. And this condition simply says that the linear transformation, I'm going to use a short form for linear transformation LT, it means it preserves scalar multiplication. Okay, a very, very important fact which is related to this linear transformation is that if T is a linear transformation, so that means I have a transformation, a mapping from one set to another set, then if it is a linear transformation, it will map the zero element of this to the zero element of the other set. So it's, say, one set, say set, K, and this is another set, say, L, or say D. So when I say T is a linear transformation, that means it is mapping the zero element or the zero vector to the zero vector of the codomain of T. Remember, T will have a domain. D is a transformation, and it's a linear transformation going to the codomain. So I'm calling the domain the set K. It's a transformation. Transformations can be is always from one set to another, with a rule in between. And codomain here can be, say, set D. Okay. So elements of the domain of T are called the vectors, as I've already said. Now, if I want to prove that something is a linear transformation, I don't want to do it separately, like do the vector addition separate and scalar multiples separate. I can actually do them together. So if I say I have two vectors in the domain of T, and for some scalars C and D, then T of Cu plus dV is C times Tu plus D times dV. So basically, I have combined these two conditions. And later on, I will show you an example. Okay, so it's not only this T, the linear transformation only works on two elements of the domain of T. It can work on a finite set of elements of domain of T. So T of C1 V1 plus C2 V2 dot 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 plus Cn Vn is the same as C1 T of V1 plus C2 T of V2 plus dot 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 Cn T of Vn. Okay, let's look at very specific examples of this linear transformation. We're going to prove that it's a linear transformation here, by the way. So, I say give a scalar r, and we define a transformation T from r squared by r squared, where every element of T, when acts on x, is scaled down by Rx. Then T is called a contraction when this R lies between 0 and 1, and a dilation when R is strictly greater than 1. In other words, it's going to contract the vector x, or it will dilate the vector x. Now for R equals 3, we would like to show that T is a linear transformation. Okay? So in order to prove it's a linear transformation, we just have to prove T of Cu plus dV equals c times tu plus d times dv. Remember, c and d are scalars and u and v are any vectors in R squared. So now here we're taking a very specific, we're saying t is a mapping from a two-dimensional space to a two-dimensional space. So here I am literally defining what my sets are. Okay, so we have to prove this equation of, that is, t is a linear transformation. So let's look at t of cu plus dv. What is this t doing? So this t is basically scaling it, and it scales it by a factor of 3. So whatever is inside, you multiply by 3. So 3 times cu plus dv, which is 3 times cu plus 3 times dv. Okay, basically I'm just simply doing simple math. And then 3 can be taken inside. Remember, c is a scalar, 3 is a scalar. We can interchange all these matrix properties, and 3 and d can be interchanged. So we have c times 3u plus d times 3v. And then 3u is nothing but t of u, and 3v is nothing but t of v. So clearly, we have proved that t is a linear transformation. Okay. Now, let's look at some harder problems. If t is a linear transformation from R squared to R squared, which maps? Okay, it maps the vector u into 2 and 1, and it maps the vector v, 1, 3 into minus 1 and 3. Now here literally I'm writing down the vectors. Okay, what does that mean? I have a transformation. As usual, it's better to make little graphs. So I have a linear transformation from R squared to R squared. It maps u. U is a vector in the domain of t, which is 5 and 2, and maps v, which is again a vector in the domain of t. So these u and v, remember, are in the domain of t. And when t acts on this, it takes us to, and t maps u into this. That means t of u. So when t maps u into 2, 1 means t of u is the vector 2, 1. Now this 2, 1 is in the codomain of t. Guys, keep in mind. You have to look at the bigger picture. Very important. Which vector comes from which vector? Because the codomain and the domain of this linear transformation are the same. These are the same dimensional spaces R2. So you have to be very careful when you read the problem, which vector belongs to which. In other words, the vector u and v are in the domain of t, whereas the vector 2 and 1 and minus 1 and 3 are in the codomain of t. Okay, so it says tu is 2, 1, and it maps the vector v into minus 1 and 3. So t of v is minus 1 and 3. So minus 1 and 3 and 2 and 1 are in the codomains of t. Rather, I would say it also is in the range of t. Okay. At this point, just remember we have a domain and a codomain, and we'll keep from there. Okay, now the question is, use this fact that t is linear to find the images of t under 6u minus 5v and a linear combination of these two, which is 6u minus 5v. Okay, now let's go ahead to keep this handy with us. T of 6u. Now t is a linear transformation. That means we can pull the scalar out. It's going to be 6 times tu. Now remember, what is tu? It is the vector 2, 1. So 6 times t of 5, 2. Remember, 5 of 2 is the vector u. And t of 5, 2 is 2, 1. And when 6 multiplied to this vector, we get 12 and 6. In a similar fashion, we can find t of minus 5 and v. So it is basically minus 5 times t of v. And what is our vector v? It is element 1 and 3. And when t acts on the element 1 and 3, it gives us the element minus 1 and 3. And when minus 5 is multiplied, you get 5 and negative 15. Okay, now let's look at the last one, t of 6u minus 5v. It's the same as 6 times du, because here we are applying, the definition of linear transformation, minus 5 times dv. And we already have got the values 12 and 6 plus 5 and minus 15. So the final answer is 17 and negative 9. Okay, now let's look at another question. These are all examples, guys, I have taken from your book, and these are in the sections, the questions which are part of that section. Okay. Here we have a question which says T is a mapping from R squared to R squared, and it's a linear transformation. It maps E1 into Y1 and E2 into Y2. Now E1 is the vector 1 and 0, and E2 is the vector 0 and 1. If you look at these two, and I put them together, 1, 0, 0, 1. This you see are the columns, E1 and E2 are the columns of the identity matrix. It's a very important fact, guys. Keep that in mind. We'll be using this in the next section also. Okay, so at this point, we are just trying to, match things with things we already know. So here what we have seen is if I have a linear transformation which maps the E1, now remember E1, we are assuming our E1 is the first column of the identity matrix, to Y1, which is minus 2 and 1. Then it maps E2. E2 is the second column of the identity matrix into Y2, which is 3 and 7. So T of E1 is minus 2 and 1. T of E2 is 3 and 7. The question is find the images of x1 and x2 and minus 1 and 5. Now find the images means this. So if I have a transformation, so the element x1, x2, it says find the images of this. That means I want to find T of x1, x2. That's what the question is. Okay, so x1 and x2 are elements of the domain of the T, of the linear transformation. Where when I say find the image of this element which is in the domain of T, basically I want a vector in the codomain of T. That's what I'm saying. Okay, so find the image of this. So what basically it means is, here, so let's go back here and solve it slowly. So T of x1 and x2, remember this one, guys. So here is my transformation. I have an element, x1 and x2. And when T acts upon it, I get the element T of x1, x2. So I want to know what it looks like. Okay, now let's go and look deeper into it. Now let's look at the vector x1 and x2. My vector x1 and x2 can be written as x1, 0 plus 0, x2. So basically, I'm writing it as a sum of two vectors. It's all things we have learned way, way early in this linear algebra class. Okay. Now, T of x1 and 0 plus 0 and x2. Now I can take x1 out and write this as x1 times 1 and 0 because x1 times 0 is a 0. So x1 0 is now written as an x1 times 1 0 plus x2 times 0 1. Now from here, when we go to the next step, this to this, I'm applying that T is a linear transformation. As it is a linear transformation, it will preserve the vector addition. That's why I can write this as T of x1 when times 1 0 plus T of x2 times 0 1. That's the vector I'm talking about. Now let's look at this one. Again, when T acts on a scalar multiplied to a vector, because T is a linear transformation, again what happens? I can pull the scalar or x1 out and write x1 times T of 1 0. In a similar fashion, when T acts on x2 times 0 1, I can take the x2 out. We get T acting on 0 and 1. Now remember, we learned from the things which were given to us in this problem that t of 1, 0, here it is. Remember, t of 1, 0 is minus 2 and 1. So that's what we're going to replace here. T of 1, 0 is minus 2 and 1. T of 0, 1. Let's go back. T of 0, 1 is 3 and 7. So replace that here. 3 and 7. Now once again we can just multiply the scalars inside. What do we get? Minus 2x1 x1 plus 3x2 7. And now we just do add of two vectors, minus 2x1 plus 3x2 and x1 plus 7x2. Okay, so that was for any element. So this x1, x2 is any element in the domain of this T, right? This, remember, is domain of T. Now, if I look at a very specific vector, minus 1 and 5. So I have already got the formula here. So remember, this one is what? T of x1, x2. So replace x1 and x2 by minus 1 and 5. And wherever on the right hand side, replace x1 by minus 1 and x2 by 5. So when you plug these values here, what do we get? Oh, need to remove this one. This was not T. 13 and 36. Okay. Now one more example, guys. No, not one more. Another two, three examples more. We need to do a little bit more work in this one. Okay. So what is this? This question is again one of the questions from your book. It says if T is a mapping from R squared to R square and it is a linear transformation. Now it is mapping a vector x into x1 v1 plus x2 v2, where this vector x is composed of the scalars of this linear combination of this element we have here, x1 v1 plus x2 v2 is this. And the element v1 is minus 4 and 1, and the element v2 is 3 and 5. We would like to find a matrix A such that Tx is Ax for every x. Okay, let's come back over here. We said that T is a linear transformation. So T is a mapping from R squared to R squared. And this question says we want to map in such a way when I write Tx, which is equal to, we have to find Ax, and we are defined that any vector x, which is in the domain of T, is mapped to x1, v1, an element of R2, which is a codomain. So what basically this is what is it. Okay, let me draw the graph here. So I have an element x here. And this x, remember, is x1, x2. And when T acts on this, it takes to an element which is given by x1, v1 plus x2, v2. Okay. We are asked to find a matrix A. So the question is, find this matrix A such that this is going to be always true. You're mapping any vector in the domain to a linear combination which is given by this relationship. Okay, let's look at this one. So we are given that T of x maps x into this linear combination. Now notice this is a vector equation. Now this vector equation we can easily write into a matrix equation. Okay, now replace the matrix in this matrix equation v1 and v2 by the values given to us. So minus 4, 1, 3, 5. And clearly this is a matrix A. And that's it. Notice in these problems what I'm always going is I'm relating back to the things we have learned. Matrix equation, vector equation, transformation, linear transformation. All these things we are learning again and again, and I'm using it in so many different forms. But the most important part is the definitions of everything we have learned. Specifically, when I do a recap, guys, I'm basically trying to say, make sure those things are, you are clear-cut, practice and practice. Okay, now we have two more examples. Yeah, two more examples, guys. Now it says, prove that the following transformation T is linear. This T is an element acting on x and y equals x minus y and 3x. Okay, I'm giving more information here. So this T is a mapping from r squared to r squared, where x and y, just to save space, guys, I wrote like that. This x and y basically means T of x and y. And this one is basically saying x minus y and 3x. That's what it literally means. And when you look at this one, that means T is a linear transform. You have to prove that this transformation is linear. And transformation means a mapping from one set to another set. So when I look at it in this form, I see it's an element of R2 going to R2. To prove that this is a transformation, that means this is linear. Remember, it's a transformation. The word is prove that this following transformation is linear. There's a difference between transformation and a linear transformation. Transformation is any general mapping from a set to set with certain rules. A linear transformation adds more constraints. It says that transformation preserves vector addition and preserves scalar multiples. So in other words, if anything is linear, what do we have to prove? We just have to prove this formula, T of C times U plus V times D, or dV doesn't matter, whichever you put first, is C times T of U plus D times D of V. That's what it says. Okay, now remember, U and V are vectors in R2. So if I'm taking U a vector x1, y1, I'm writing it like, just to save space, guys, I was writing in a row vector form. It can be also written as a column vector as x1, y1. And have another vector v in R2, x2, y2, it says x2, y2. And I'm taking two scalars, c and d. So T of cu plus dv is T times c of x1, y1 plus d of x2, y2. Now c is a scalar multiplied to every element inside the vector. So it is cx1, cy1. Similarly, it is for dx2 and y2. Okay. Now, I will just show it to you. If you get confused, you can write it in the vector form. It's T of cx1, cy1 plus dx2 and dy2. As I said, I'm just saving space. That's why I wrote it like that. Okay, now these two I can add the first, because it's a sum of two vectors, cx1 and dx2, that's the element here, and cy1 plus dy2, that's the second element of the vector. Now when t acts on it, we have defined that txy goes x minus y 3x. That means the first element, or the first row and the column vector in the column, we will subtract that from the second one. That means we are going to take the element cx1 plus dx2 and subtract cy1 and dy2. So that's what it is. We're applying the definition here. And the second row in that column will now be multiplied by 3 to the first element, or the first row of that column. So it's 3 times cx1 plus 3 times dx2. Literally, you're just following what the rules are given to you. And after that, it's simple algebra. Now we want to have something called c times tu. Tu means x1, y1. Now gather all the x1s and y1s together. So cx1 minus c1, and then dx2 minus dy2, and then 3cx1 plus 3 dx2, and then remember it's a sum, so this, and then so it's a vector here, so I can show you if you want to write it down here. This is basically cx1 minus cy1, one element, plus dx2 minus dy2, that is the first row of that column vector, and the bottom is 3cx1 plus 3dx2. Now that's this. And then I can pull them apart, cx1s together and the d's together. So cx1 minus cy1, 3cx1, and then plus d of x2 minus dy2, 3dx2. So take the c out, so it's x1 minus y1, 3x1. Basically this is t of u, so this is u. When you add t on it, it will give you x1 minus y1, 3x1, and similarly d of x2 minus y2, you get this. This automatically proves that this t is a linear transformation. Okay. If we can prove something is linear, we can prove something is also not linear. It's much more easy to prove something not linear than linear. Because if you are going to prove something is linear, you have to do a very general proof because it has to be true for every x and every y's in the domains and codomains. Whereas if something is not linear, one simple example is more than enough to prove that this transformation is not linear. Okay guys, so let's look at that. Prove that this following transformation is not linear. I just chose the easy one. I just went for the scalar multiplication. I said let's take a vector u, 3 and minus 2 in R square, and see a minus 1 is a scalar. So t of c of u, that means minus 1 times the vector 3 and minus 2. So you multiply minus 1 to the vector inside, you get t of minus 3 and 2. And according to the formula, so x goes in the second row and becomes a square. So minus 3 square is 9. And 2, which is, here, goes as the first row element of the, when t acts upon minus 3 and 2. So that's 2 and 9. Now, if it is a linear transformation, then c times tu should always be the same. So let's look at that. So minus 1 times t of 3 of minus 2. Now remember, when t acts on 3 and minus 2, we get minus 2 and 9. That's how it is defined. Because minus 2 goes here in 9, and then when minus 1 is multiplied to this, we get 2 and minus 9. Clearly, these two are not equal. And therefore, t is not a linear transformation. So remember, it is easy to prove something is not linear because you just have to get one simple example, plug in numbers and show that. At the same time, be very vigilant. If you have to prove something is linear, you have to prove for every element of the domains and the codomains. Very, very important. Okay. Now, as the way we normally do our scenarios here in our sessions, the very last slide, I would ask you guys to do some practice problems. They are coming from section 1-8. So 17, 19, 21, 22, A to D, and 24. I would guys like you to practice these. Thank you.